Thanks for joining in, and hello. I'm Faz, and I'm a developer specialist solutions architect for the DevOps team at Amazon Web Services. And today I wanted to share on startups moving from monoliths to serverless. In this session, we're going to talk about what a startup's product roadmap looks like, how delivering fast matters, how different architectural patterns lend itself to different phases of a startup, how to migrate from one to the other, and how serverless allows you to focus on delivering business value faster to your customers. When you're building products in a startup, you have certain constraints that you're working with. The chart here shows a specific constraint that impacts a startup, the end of runway, which basically is how long your company can survive in the market if the income and expenses remain constant. Each bar represents a feature, and the length of the bar represents the time it takes to build the feature. Too often, startups are building features too far in the future. You're moving so fast in different directions that the future you're planning for now is not proven to materialize. Future planned work is usually bigger, meaning a disproportionate amount of your effort will take time, if ever, to return value. The biggest problem, though, is that many features are built to return value after you have run out of money. Remove the undifferentiated work, postpone work needed for the future, and focus on delivering features that your users are asking for now. These will be faster to deliver and will make it more likely that you will find product market fit before the end of the runway. Our goal at AWS is to automate and abstract away as much of the undifferentiated work as possible so that our customers can focus on building applications for their business. And herein is where we truly are witnessing a paradigm shift, that it's driven by our customers working backwards from what they need to do to win in the market. Businesses want to win more customers. And to win customers, they need to build better products and to release features faster, which requires faster and more frequent experimentation and innovation. They need the ability to focus on differentiating by business logic. We no longer live in a world with a single database or architectural paradigms. And AWS is providing ways for customers to shrink the scope, offload the undifferentiated pieces, choose the right tool for the job, and automate everything. By doing so, customers can build modern applications that allow them to win more customers. Also, as you go knee-deep into product development, you discover that building is fun, but maintaining is not. It might seem easy to build something initially. However, this approach does not scale well. Everything you build, you will have to maintain. And you have to make sure it runs well in production without disruption to your customers. You probably have the capacity to build one great product. Once you have a successful product your users love, and as you continue to grow, you will have big, interesting technical challenges to overcome. There will be operational challenges when making quick changes and scaling the product for an increasing customer base. By building less, you will maintain less and deliver more to your users. Undifferentiated lifting is hard and unnecessary. Using services means you don't need to provision infrastructure or scale instances. Accelerate the speed of development and pay for the value you use by using AWS services, while having secure and highly available characteristics built in. Jeff Bezos, the CEO of Amazon, said about product building, the reality, of course, today is that if you come up with a great idea, you don't get to go quickly to a successful product. There's a lot of undifferentiated heavy lifting that stands between your idea and that success. So with this, let's have a look at what an architecture a startup would predominantly start with, a monolith. A monolithic application describes a single code-based application, usually in a 2 or 3-tier architecture, in which the user interface and the data access code are combined into a single program from a single platform. This application does everything with every single capability built into a single system. And there are a number of advantages of developing monolithic architectures. Because you have a single code base, this provides good IDE support and makes it easier to develop, debug, and deploy applications. A well-designed monolith that takes care of state management appropriately can be scaled horizontally by running multiple copies of the application behind a load balancer. And it's okay to start with a monolith. Now, as your business grows, you start seeing limitations to the choice of using a monolith. Let's face it, no system design is perfect. And with monolithic architectures, there are a number of limitations associated. Firstly, you can't make a change to one part of the app without full regression testing of the entire application. As a result, development typically slows down. You also have a single release pipeline that may take hours to deploy and traditionally requires manual user acceptance testing, which also slows down the deployment cycle. Once in production, you find scaling monolithic applications horizontally becomes challenging, especially when it comes to managing state. You also see monolithic architectures typically requiring a long-term commitment to a technology stack, which can stifle productivity and innovation. So how exactly do microservices solve some of these challenges and help you become more agile? Let's firstly understand a microservices architecture. Microservices are a polyglot technical stack comprising of small, loosely coupled application components that are developed, deployed, and operated independently by small teams. These applications also leverage decoupled data stores, in which there is a one-to-one mapping of database and microservice. Being a polyglot design, you get to choose the right technical stack for each part of the application. So if it makes more sense to use Rust in one microservice because response time is important, and to use Java in another microservice because of dependencies on some third-party jar file, you are not locked into a one-size-fits-all implementation. You also have polyglot data persistence, so you can ensure you are using the data store for each microservice that is fit for use and fit for purpose for the way the data needs to be accessed by clients. Keeping these architectures in mind, let's look at the different compute options available. On AWS, we have customer applications that can broadly be categorized into three types, based on compute. You have server-based applications that use a virtual machine instance wherein you are abstracted from the underlying hardware. Then when you move up the stack, we see containerized applications where the operating system has been abstracted from the rest of the stack, which allows you to package applications and the dependencies together in a container for easier deployment. Then we have serverless applications where you don't have to manage any of the underlying infrastructure and just focus on code or containers as the unit of work. And with the serverless approach, you have no infrastructure provisioning and no management overhead of that infrastructure. You get automatic scaling as part of the setup and you pay for value. Serverless applications also become highly available and secure since the underlying infrastructure is managed by AWS. So when you build out serverless applications on AWS, you build high-level purpose-built services. The code is almost exclusively business logic, which reduces the amount of boilerplate code you need to add to make it work. And with the pay-per-use pricing, you only pay for when the application is invoked, not for idle time. This leads you to a greater peace of mind. Thinking of serverless from an operations perspective, you see that serverless means that you never have to patch another OS. You never have to be paged when a system goes down. You never need to roll out software as part of deployment to multiple nodes. You never pay for idle infrastructure. And you never lose business from your customers because you can't scale. Werner Vogels, CTO of Amazon, said on serverless, "No server is easier to manage than no server." And with serverless on AWS, because we handle the undifferentiated heavy lifting of the infrastructure, you get to focus on what values the most to you, your customers. With serverless on AWS, you see it is more than compute. While many customers associate serverless with Lambda, there are actually serverless services at all layers of the stack. While Lambda offers many key advantages for our customers, it's really when all these other components surround Lambda that we start to see much bigger benefits. Messaging, orchestration, storage, and compute together are the secret sauce. But in fact, it's really when all these components come together that we really start to see big gains. When getting started with serverless, you can have a simple architecture to start with. A RESTful microservice could just have an API endpoint that is powered by API Gateway. When invoked by a mobile app, API Gateway will invoke a Lambda function with your business logic and read or update status in a database, which in our case is DynamoDB, a NoSQL database service. Scaling the serverless microservice architecture is easier with various clients, potentially including other microservices, communicating with the services, and a polyglot of data tier components used to read and update data. Adding in a traditional service like a relational database hosted on RDS also works well in this serverless architecture. You still have your business logic interacting with the relational database and the other data tiers while accepting requests from an API gateway. You may also host a static website from CloudFront, a content delivery network service that caches the website assets from an S3 bucket. The core business logic used can be stored in Lambda's functions, or you can replace it with business logic deployed in a container. In this case, even with the container being deployed on a container service like Elastic Container Service, you still get to integrate with the same services as before with minimal changes to the code. So, what options does AWS provide for serverless compute? When looking at serverless compute options, you have a choice between using serverless functions or serverless containers. At one end, we have AWS Lambda that starts, stops, scales automatically based on the parameters defined. AWS Lambda is a great choice for applications that don't have specific infrastructure requirements. Because it is event-driven in nature, AWS Lambda is also a good fit for data-driven applications that need to respond in real-time changes to data. At the other end, there is AWS Facade, a serverless container service where you have a completely managed infrastructure for running containers. You can run containers without having to manage servers or clusters. You don't have to worry about patching or upgrading or how to pick the right instance type or instance size. You want to leverage AWS Facade when you need support for long-running compute jobs, and when you want fine-grained control of the compute resources allocated to each task. Werner Vogels also said on serverless, going serverless frees you to focus on activities that set your company apart, like product innovation. After covering the compute options, let's talk on how one can move from a monolith to a microservices architecture. While there are many approaches to migrating a monolith application to a microservices architecture, there is a popular approach commonly called the strangler pattern. Martin Fowler, chief scientist at ThoughtWorks, said on the strangler pattern, an alternative route is to gradually create a new system around the edges of the old, letting it grow slowly over several years until the old system is strangled. Let's walk through at how we can use the strangler pattern to migrate the current application that has a standard two-tier architecture consisting of a web and app layer and a database layer. This is a monolith application because the web and the application layer are tightly coupled together with the database. The first step we take is to have a Facade API in between the client application and the load balancer. This allows you to shield your users from any changes behind the scenes and not disrupt them with frequent client application updates. Next, we need to identify what part of the monolith needs to come out first. An approach here can be to detect and measure hotspots throughout the monolith application to identify any function that has performance issues. You can also use our observability service, X-Ray, to trace function calls from the API gateway downwards to detect hotspots. With the hotspot function found, let's move it into a Lambda. Also to note that in a microservice architecture, each microservice has its own data layer and nobody accesses that data directly. It is all done via an API. Now each database can be scaled independently according to the needs of the business without this affecting the rest of the system. Having a decoupled architecture for databases also gives teams the flexibility to choose the database that is best suited to the service they own. For example, some services are better suited to a relational database. Say the microservice requires atomic transactions. Your developers are free to use a relational database management system for that microservice. Alternatively, another microservice may not need relational mapping and is better for a document store, leveraging the NoSQL pattern. In this case, we create a new DynamoDB table, which will be part of the new hotspot microservice. Data is synced from the relational database to DynamoDB using database migration service that allows you to capture data changes for any updates happening in the relational database and propagate that to DynamoDB. Now, as you notice, nothing has still changed in the monolith because the Lambda is not receiving any requests to handle. Let's change that. For the API route that was invoking the hotspot function in the monolith, we point that route to invoke the new Lambda. Now, to test if this function is working as before, we want to send only some of the user requests across. This can be done by doing a Canary release deployment on API gateway and setting it to send 10% of the user traffic every hour. With this setup, you can then test and monitor the behavior of the Lambda to ensure it is executing the business logic and operating on the data as it is supposed to. After the test metrics pass your requirements, you can promote the Canary release to the production release and disable the Canary from the deployment. With our first function carved out, we start looking at other functionality that can be transformed. Perhaps the underlying database layer needs to be modernized, wherein you move to a modern database like Aurora that scales compute and storage independently. We follow a similar approach as before, and this time host the extracted application code on EC2 instances because of certain dependencies we want to control at an operating system level. And we continue this process until the monolith disappears, not with a bang, but with a whimper. What you now have is a microservices architecture leveraging services on different compute platforms integrated with polyglot databases to use the best data store for the use case. Adrian Cockcroft, AWS's VP of Cloud Architecture Strategy, said on Serverless, "Serverless is the fastest way to build modern applications." Next, we have with us Asyrique, CTO and co-founder of Vase.ai, to share more on their monolith to serverless journey.
Thanks, Fuzz. Hi, I'm Asyrique. I'm the technical co-founder and CTO at Vase.ai. We're a real-time consumer intelligence startup based out of Malaysia on a mission to make human behavior more understandable through building better and fairer systems for collecting and compensating humans for the data they share, and then analyzing it in aggregate to help companies and governments build better products. Here's an overview of how our journey from monolith to serverless has been at Vase.ai. To set the scene, here's another quote from Martin Fowler's article on Monolith First. He says, "Almost all the cases where I've heard of a system that was built as a microservice system from scratch, it has ended up in serious trouble. This is why I'm a firm believer in always going monolith first. When you're shipping in a startup, network effects, money, and reach are against you. The only way to succeed is by running hard and out-executing the bigger guys. During this time, stick to your monolith. Monoliths are great for adding new functionality, easy to test, easy to vertically scale, both from a workload and team perspective, and easy to reason about and develop on. Resist the urge to break your monolith into services until the last possible moment so you have the most uncertainties figured out. Here's what our monolith looked like up until mid-2019, which is when we began our monolith to serverless journey. This was 4 years after Vase.ai was founded. So now that I've made sure you always go monolith first, here's some signs that your app might be ready to transition to serverless. Firstly, if your traffic to your app is bursty, it's 1,000 requests a second 1 second and 0 the next, that's normally a good fit for serverless. It's also a good sign that an app should be broken down into serverless functions when different parts of the app have different scaling requirements. Maybe your web request handler needs lots of compute but low memory per invocation, while your data layer needs lots of RAM but only gets invoked once a day. This is a good sign these two parts of the app should be separated into 2 or more serverless functions. Thirdly, if you're on AWS, you probably use a bunch of their services, and sometimes you need glue to connect one service to another. For example, we use a serverless function to pipe SES events into our database for long-term storage and analytics. Finally, as your team grows, you'll find engineering teams being split by domain, like the creation of a payments team or a real-time collaboration team. And it makes sense to pull apart your monolith along the interfaces of these teams. Once you've decided an app is ripe for transitioning to serverless, there's generally 2 ways to approach it, starting with the hottest end or the coolest end. Starting from the hottest end, the most often executed code paths means quick feedback if something is broken, and lots of test data. But starting from the cold end has its own benefits too, namely lesser risk due to lower invocations, which gives you more time to test stability. At Vase.ai, we decided to alternate hot and cold down to the middle. Our hottest function, being called thousands of times per second, was the function that retrieved the next question for a respondent to answer, while our coldest function, which generated PowerPoints for export from the data, it's called around once a week. Here's what our platform looks like today, as we're nearing the completion of our serverless transition. So, as you saw in the previous diagram, our main data collection is fully serverless on Lambda. All our services have been split along interface lines into stateless functions or containers as much as possible, and all apps publish and subscribe to the event bus, which is using Redis streams as an append-only log of events. Since we're a full-stack JavaScript shop, writing code around an event-driven runtime like Lambda actually came a lot easier to my engineers. And these days, Lambda is our preferred choice when prototyping new MVPs or application logic. We're also constantly running experiments on how to make user experience better and faster. And I listed out 2 of the current experiments we're running on Lambda now. But while it's been a great experience running our platform on Lambda, there's always the flip side. As with any decisions in tech, there's always some gotchas to watch out for. The important thing is to know and plan for them. So let's dive in. First up, given the evented nature of serverless Lambda, it really only makes sense to use either RPC or event bus to communicate between your services. Using a DB can lead to all sorts of race conditions and is a recipe for sleepless nights. Next up, as serverless functions optimize for speed of execution, large traffic spikes will cause thousands of functions to spawn, and if you don't carefully tune your DB, it could cause it to fall flat under load. It's also important to ensure how your serverless function communicates with each other is well documented and updated whenever there are significant changes to your functions. You will also want to architect your serverless functions to be as stateless as possible. Serverless excels at horizontal scaling, and statelessness is a key part of horizontal scaling. Finally, I'll leave you with some hard-won knowledge on characteristics that don't make for a good app to port to serverless. If your app is licensed per core and Lambda spins up 1,000 functions simultaneously to handle extra load, boom, you're now on the hook to pay for the licenses for 1,000 cores. Also, any app that requires specialized computing hardware beyond regular compute or RAM for now, it's better to not go with serverless. This is also the case for apps that don't inherently have any parallelizable components, which are what can be split out into serverless functions. Finally, apps that can't be restructured into a more event-driven architecture make bad candidates for breaking up into serverless functions. Thank you and enjoy the rest of the session. Back to you, Faz.
Thank you, Asyrique. Great example from Vase.ai there. As you saw, moving from monolith to a serverless architecture allowed Vase.ai to innovate further in delivering better business value for their customers. Andy Jassy, the CEO of AWS, said, if Amazon.com were starting today, it would go serverless. When looking at AWS's offerings on serverless, you will see that AWS has provided serverless at every layer for the customers. Starting with compute, we have AWS Lambda as a compute platform for functions, AWS Lambda at edge for functions at the edge, AWS Fargate for serverless hosting of containers, Amazon API Gateway for deploying APIs that connect to different backends, and AWS Step Functions, a serverless orchestration service for microservices. In storage, we have Amazon DynamoDB, our fully managed NoSQL database, Amazon Aurora Serverless, our on-demand relational database service, Amazon RDS Proxy, a fully managed database proxy feature of RDS, Amazon S3 for object storage that provides 11 nines of durability, and Amazon Elasticsearch. In messaging and streaming, we have Amazon SNS, a notification system that can notify through email, SMS, and more, Amazon SQS, a message queue system, Amazon Kinesis data streams and Firehose for handling real-time streaming data, Amazon AppSync, a service for developers to manage and synchronize mobile app data in real time, and Amazon EventBridge, a serverless event bus to connect applications together. In user and identity management, we have AWS Cognito, a service to handle user sign-up and authentication, and AWS IAM that manages access to AWS services and resources securely. In delivery at the edge, we have Amazon CloudFront, our CDN service, and Amazon API Gateway, edge optimized. In analytics, we have Amazon Kinesis Data Analytics to analyze streaming data, and Amazon Athena, a serverless querying service to analyze S3 data using SQL. In provisioning and monitoring infrastructure, we have AWS SAM, a framework to manage serverless applications, AWS Amplify, a set of tools and services to accelerate development of mobile and web applications on AWS, Amazon CloudWatch, a service to monitor AWS cloud resources, AWS X-Ray to help developers analyze and debug distributed applications, and CDK open source software development framework for defining cloud infrastructure as code. In development tools, we have AWS Code Commit, a managed source control service, AWS Code Build, a fully managed continuous integration service, AWS Code Deploy, a service that automates code deployments, AWS Code Pipeline, a continuous delivery service, and AWS Code Artifact, a fully managed artifact repository service. Here at AWS, we have more than a decade's experience helping customers break down their monolithic architectures. And there are a number of best practices that we have learned along the way from companies who have successfully made this shift. The first key point to make is that successful migrations from monoliths to microservices are accompanied by a cultural shift. It's not just about the technological change of refactoring monoliths and decomposing databases. Companies should focus on removing silos between teams, granting individual teams with greater ownership, and assigning a team that can oversee the entire development management and operation of microservices. Another organizational change that is typically required is the adoption of a mindset that security is everyone's job. For a long time, developers were primarily focused on functionality, and once the features were baked into the application, they'd hand it off to someone else to implement the security components. That will simply not work in a microservices architecture. Everyone needs to have a stake in security, and it needs to be factored into every decision that is made about how the applications are built and updated. Last but not least, it's important that leadership continues to paint the big picture and provide visibility of the work that's being done and how that is helping to drive business outcomes. The second aspect of successful microservices deployment is implementing robust DevOps practices. We could spend an entire session just talking about best practices, but I wanted to highlight a few here. The first is clearly defining your APIs. API design principles should be simple and consistent to make it easy for your developers to follow. That means adhering to API resource naming conventions, such as using nouns to represent a resource, HTTP methods to supply the action, and using camel case for resources requiring more than one word. There should be clear guidance around versioning, and all APIs must be documented. These days, continuous integration and continuous delivery are the bread and butter of software delivery to enable rapid feature development while still maintaining system stability and security. All applications will fail at some point. It's simply inevitable. We like to say design for failure and nothing fails. If apps are not designed to be deployed easily when they do fail, the result is problematic downtime. Microservices enable continuous integration and continuous delivery, allowing you to deploy applications easily and repeatedly. This makes it simpler for your team to try out new ideas and to roll back if something goes wrong. The low cost of failure enables experimentation, makes it easier to update code, and accelerates feature velocity. Of course, organizations also need tools that help them adopt modern application development techniques so they can get the most out of the cloud, ranging from CI/CD to infrastructure as code solutions, monitoring, logging, and tracing. Anything that is a manual process that can be automated, we automate. We find not only does this bring incredible benefits to speed, but it also increases uptime and reduces errors. So, to get you started, here are some resources. Have a look at the Amazon Builders Library, a collection of real-world practices and guidance from Amazon's leading engineers on how to build modern cloud applications. The library covers architecture, software delivery, and operations practices. Here are some examples of the Builders Library content, and to see more, visit the link below. You joined AWS Summit to learn, and you can keep learning beyond the summit with resources from AWS Training and Certification for DevOps. We offer over 45 online digital training that is available on demand. You can go deeper with a 3-day instructor-led course, DevOps Engineering on AWS. You can gain credibility and confidence with 2 related certifications. You can also explore labs, white papers, and other technical resources by downloading the AWS Ramp-Up Guides. For more information, visit aws.training/DevOps. Thanks for listening to today's session. I hope you enjoyed it. And please complete the session survey with your feedback.